Yes. In case you weren't all sick of my voice, I'm sick of my voice. Okay. Yeah, so this time I'm talking not so much about its general circulation, but how it varies on shorter timescales. So sort of annual to decadal kind of timescales. And this is an interesting question because it really impacts the climate that we're experiencing sort of now. And if we want to make predictions, so if we want to make predictions for the next 200 years, we just have to worry about mostly the anthropogenic part. But if we want to make predictions for the next decade or so, we also need to really worry about the internal variability. So that's why we're interested in these kind of modes. So what I'm going to talk about a bit is where the climate varies and where we think it might be predictable, and the different modes that might be causing that. So I'm going to talk about the impact those modes have in the current climate, according to observations that we have now, and also a bit about how they might change in the future. So this is a plot of the amplitude of variability. I apologize for those of you who hate the rainbow color scale. I love the rainbow color scale. And this is a work in progress. You know, it's not published, so I didn't have to convert it to a non-rainbow color scale for all the rainbow haters out there. So this is just a plot of, you take annual surface air temperatures and remove the force signal or some estimate of the force signal, and then just calculate the amplitude of what's left. So, you know, it's a pretty familiar picture. You have larger amplitude variability over land than over ocean on average. This is from observation, so anything in the southern hemisphere is not particularly reliable. I mean, the far south southern hemisphere. You can see a bit of amplitude variability here, which is probably related to El Nino. Well, definitely related to El Nino, and a few other patches of the ocean as well. And if you start looking on longer time scales, so on 5 years, the 5-year time scale, you still see El Nino. Once you've gone out to 40 years, now definitely don't trust anything at high latitudes, north or south, because we don't have great observations, like long enough time series of observations. Even these, in fact, I don't know why I show this plot at all, it's so unreliable. But there are particular patches that do pop out. So if we're looking just at the oceans, you can see there's something here in the North Pacific, maybe a bit in the North Atlantic. So basically, I'm just trying to point out that different parts of the ocean have variability on different timescales. And if we can predict that variability, understand it well enough to predict it, then that would be quite nice for climate predictions. So if you look at the same picture for models, where we do have longer time series, so it should be a little bit more reliable, although it doesn't match up exactly with what you see in observations, which is a whole other question. But so you still have this sort of area here in the tropical Pacific, which shows up on the shorter time scales, and on the longer time scales, you have stuff in the Southern Ocean, you have stuff in the North Pacific and North Atlantic. So we'll talk a little bit about those today. So what does that mean for predictability? So this is a plot from the IPCC where they took a whole bunch of climate models and they did initialized predictions with them. So they all start from some approximation of observations and they run into the future. And the speed with which they diverge, or the ensemble diverges, gives you an idea of how much predictability. So if all the ensemble members are completely different from each other within 5 years, you think, okay, there's no predictability. But in some places, if they sort of go along the same trajectory for a little while, there must be a reason for that. So we think there might be potential predictability in that region. So this is a plot of the potential predictability variance fraction for 5-year mean temperatures. And you can see you get predictability much more over the oceans than over the land on these sorts of timescales. And again, there's the North Pacific that pops out, the North Atlantic, and something in the Southern Ocean. So we suspect that it must be due to internal ocean processes, which happen on slightly slower timescales, that's giving us those predictability. So we associate them with modes of variability. just for comparison, if you do the same sort of study but with forced variability included, this is the predictability you get for the forced component. And when you first look at it, you think, why do we bother? That's so small compared to this. But if you look at the regions which it happens in, the Southern Ocean, not that much forced predictability there, and yet there is some internal predictability, same in the North Atlantic. So it's almost as if they're in competition. Well, it's exactly as if they're in competition. The more internal variability you have, the less predictability you're going to get from your forced signal, because you also have to take the internal variability into account. That makes sense. Okay, so this plot you've already seen, change in average surface temperature from the IPCC. So between the end of last century and the end of this century, the end of last century and the end of this century in two different RCPs. And the point I'd like to make here is that the background is changing. So all the modes of variability, they are occurring on the current background ocean circulation. But as we change that in future, the modes are going to be changing as well, because their background is changing. So basically, we can expect that the modes might change, the patterns might change, their amplitude might change. We might get new modes of variability. I don't know, that could be anything really. So the same plot that I showed you before, now in not rainbow color scale, the amplitude of variability from CMIP5 during their control runs. Again, large amplitude stuff happening at high latitudes, ENSO pops out here. If you do the future change in amplitude, so you do the same calculation but for the end of one of the future scenario runs, you get decreases in amplitude over the high latitudes, probably related to sea ice. If there's no sea ice, we can't have sea ice variability. And larger amplitude variability at low latitudes, particularly over land. And if you look at the relative change, so this one divided by this one, you see that in some places that's about a 40% change in variability, which is something we really care about. Like, if you think of the tropics, it's already hot, right? If you start having heat waves 40% larger than normal, that's going to, people are going to be actually really suffering. So that's just a sort of motivation, I guess, for why we're interested in studying this stuff. So now, the modes of variability that might be causing all this. This is just a little schematic that I sort of hashed together of the ones that I'm going to be talking about today. So you probably have heard of most of these. And if not, by the end of today, you will know about them all. So ENSO, El Nino, that's the most famous. Everyone should have heard of that one. Related to that, in the Pacific, but on slower timescales, the IPO, the Interdecadal Pacific Oscillation, also called the PDO, Pacific Decadal Oscillation, depending on whether or not you're from the North or South Hemisphere. The PDO was sort of discussed first, and it's sort of the Northern Hemisphere part of it, and the IPO is essentially the same thing, but looking on a sort of hemisphere-wide. So I might accidentally call it the PDO sometimes, because I did my PhD in the Northern Hemisphere and I got brainwashed. So we have the AMO, the Atlantic Multidecadal Oscillation. That's sea surface temperature variability in the North Atlantic. The IOD, related to sea surface temperatures in the Indian Ocean. And the SAM, the Southern Annular Mode, which is related to atmospheric pressure dipole over the Southern Ocean. And we're going to talk about each of those. Yes.
Which is the MJO?
No, the MJO is not on here. It's because it's atmospheric. And it's also shorter time scale. So I'm looking at things that last for years to decades, whereas the MJO, I think, is weeks or months. I'm not sure. Okay, so first of all, the Southern Annular Mode. This is the most atmospheric I'm going to get. It is a dipole of high and low pressure over the Southern Ocean. So when the SAM is considered to be positive, you have higher pressure in a belt sort of around Antarctica and lower pressure over Antarctica. And what that does is speeds up the winds. So you have a stronger westerly flow, more storms associated with a positive SAM index, and also moves the storm tracks southwards. If you plot, so they make an index to measure this variability. There's a couple of different ways of doing it. Sometimes they just take two stations that have been measuring pressure, one to the north and one to the south, and calculate the difference. Sometimes they'll do like an EOF analysis and look for this kind of pattern. But the results are broadly the same, so it doesn't exactly matter which one you pick. So this is a plot of what the SAM indexes looked like going back to the 50s. And you can see there has been a positive slope on that. So there's been a lot of studies to work out whether or not that is anthropogenic or just natural variability or some combination of the two. We can go further back in time by looking at proxy records. So this is a study which took proxy records from all these locations and calculated their estimate of what the SAM was going back 1,000 years. And you can see, so the black one is the proxy record one. The colours at the end are different observational and reanalysis products. And you can see that sort of there's been a general increase since the 15th century, basically, in SAM. So, so what are the impacts of that? Well, I talked before about the Southern Ocean and all the different processes that are going on there. Changing the winds is obviously going to change all of those processes. So if you have stronger winds, you're going to have stronger Ekman transport in the boundary layer. You're going to have stronger upwelling, which is going to change the circulation. So you're going to have stronger upwelling. You're going to change your deep water formation potentially, or intermediate water formation. So you can potentially be changing the entire ocean circulation by changing the type or rate of deep water that you're forming. So obviously this is something that's interesting, the very long timescale studies. If you start messing with your bottom water formation, then on very long timescales you are changing the circulation of your entire ocean. But on shorter timescales it also has like sort of more immediate impacts. You can regress the SAM index with temperature. So all the points show all the different stations where they've been measuring temperature. And this is correlated with a positive SAM index. So if the SAM is positive, you get warmer temperatures over Tasmania, colder over the rest of Australia, and the opposite in precipitation, similar over southern tip of South America and South Africa. So like particularly in Australia, if we're thinking of drought prediction, for example, then the SAM is something we're really interested in because it is quite highly correlated with our rainfall. So what has caused it and what do we think is going to happen to it in the future? So this is a plot. They've broken up the SAM index by seasons and they've plotted the trend per decade. So the SAM, the changes are strongest in the Southern Hemisphere summer. So the black lines here are 3 different observational products. And the coloured lines are model runs done with different forcing. So greenhouse gas, aerosols, ozone, and natural. And so if we just look at this summer one, you can see the only way we can get the models to agree with observations if we include ozone. So the theory is that it's the ozone hole, not unexpected, which has been causing most of the SAM trend that we've observed so far. So into the future, if we are, well, we've slowed down with our emission of ozone-emitting products, and we expect the ozone hole will eventually recover. But in the future, we haven't really solved our problem because greenhouse gases here also cause a positive SAM trend. So as the ozone effect decreases, the greenhouse gas effect is going to increase, and so we expect that the SAM will continue to be positive into the future. So that will have consequences for particularly Australian rainfall, for example, and in the longer term also potentially ocean circulation. The next one we're going to talk about, the next mode of variability, is the Atlantic multidecadal oscillation, or the AMO. This is a plot of sea surface temperature that is associated with a positive AMO phase. So you can see you have large positive anomalies in the North Atlantic in particular, a little bit of positive in the North Pacific, although that is a little bit more speculative because this is a low-frequency mode of variability, so it happens on the timescale of decades. So ideally, to study this, we'd want climate records which are hundreds of years long, which we haven't got. So everything begins to be a little bit statistically not quite so significant. This bit is what we're going to focus on, and the rest of the oceans, not so sure about. So I showed you a plot in the last presentation of what happens when we slow down the Atlantic meridional overturning, the plot with the big blue blob all over here where Europe gets colder. So obviously North Atlantic temperatures are something that, particularly if you live in the Northern Hemisphere, you're really going to care about. Because this overturning is linked to the, this mode of variability is linked to the overturning. And you can understand that because if you think about what overturning is happening here, it's bringing warm water northwards at the surface, it's cooling and sinking here and going southwards again. So it's transporting heat and releasing the heat here, and that's the heat that keeps Europe nice and warm. So if you slow that down, you're bringing less heat, so Europe's going to be colder. So if you plot the time series of the AMO index, so you calculate the AMO index just by averaging sea surface temperatures over a box in the North Atlantic, and then you try and remove the force signal, and this is what you have left. You can see you have, there's a lot of shorter term variability, but if you smooth it out, you get these sort of periods where it's cold for a couple of decades and warm for a couple of decades and so on. So that's also going to have an effect on European temperature and European rainfall and American rainfall. So this is a plot of its effect on rainfall. So when the AMO is positive, you have more rainfall in the Sahel, more rainfall in Europe, less rainfall over large parts of America, South America. And because it's linked to SSTs, you also have changes in hurricane activity. So this is a plot of all the landfalling hurricanes during the AMO negative period, and this is a plot during the AMO positive period. And you can just see by eye that there were many more hurricanes during the time when the North Atlantic was warm. So what's going to happen to that in the future? I showed you a plot in the last talk that had all the model simulations of what the AMO was doing, and a lot of them were sort of decreasing a little bit. So we expect that the AMO, the AMOC, all my acronyms are just confusing me. So there's the AMO, which is the Atlantic multidecadal oscillation, and then there's the AMOC, which is the Atlantic meridional overturning circulation, and they are linked. So variability in the AMOC is basically what causes the AMO. So if the AMOC decreases, what's going to happen to the AMO? So you have a steady state, you have variability about that steady state, and then you change that steady state, like you're decreasing it. Will the variability in that decrease as well? Will it have a wild last wobble until the whole thing collapses? I don't know. Models vary quite wildly on their responses to this. Some of them are very easy to collapse the AMOC, some of them seem to be a lot more robust. And observations, we don't have enough of them. There's this very neat observational campaign started in the early 2000s. So this is the North Atlantic, 26 degrees north. They went out and put a whole series of moorings across the whole basin to try and measure what the overturning is, because this is something, it's a basin integral, so you need to measure across the whole basin. So they put all those observational instruments out there. They go out every couple of years and retrieve the instruments and do all their calculations and plot this. They've broken it up into different components, but basically the one we're interested in is the red one here, which is the overturning. And so this is, 2005 to 2011. So, I mean, you can't see if there's a decrease yet. There's quite a bit of variability. And the AMO, as we saw, varies on multi-decadal timescales, which means we'd expect there to be multi-decadal variability in this as well, which obviously we're not going to see from such a short time series. So, yeah, AMO in the future is kind of a question. We don't know what's going to happen to the AMOC in the future. Therefore, we don't know what's going to happen to the AMO in the future, and every single model has a different answer. So this is a bit of a theme. You know, we don't know. The models don't agree. Sorry. Moving on. The Indian Ocean dipole. So this is a plot of sea surface temperature again in the Indian Ocean. And what has been observed is that there is often a dipole. So the western part of the basin will be warmer, or like the opposite side, warmer or colder than the eastern part of the basin. So what people do, these boxes here, they take the sea surface temperature averaged over those boxes and calculate the difference, and that gives them a time series for the Indian Ocean dipole. And this particular study, they looked at proxy records from these regions to try and calculate what the mode was back in time so that we can extend it past the time for which we have sea surface temperature observations. So the reason we're interested in this, particularly in Australia, is because this is the rainfall associated with that. When it's colder, you have less rainfall. When it's warmer, you have more rainfall. That's just over the ocean. But if you look at it over land, it also has impacts over Australia. So when the dipole is positive, it's positive. So it's warmer over here than over here. You have a reduced chance of rain over this band right over the middle of Australia. Also has effects in Africa, particularly with the monsoon. But yeah, if we focus on Australia, then it's associated with a reduced chance of rain. And the opposite, so when the Indian Ocean dipole is negative, we have greater chance of rain in Australia. So what's it going to be in the future? Well, again, I'm sorry, we don't really know. So this is the same paper I was pointing out before. They took their time series from the proxy records of what the Indian Ocean dipole has been, and they calculated the recurrence interval, so how often you get an Indian Ocean dipole recurring. So, for example, these triangles up here show when there was a strong IOD event, and so the black triangles are a strong event, and the grey triangles are a medium amplitude event. And what they showed is that the occurrence has been increasing in the last couple of decades. So we've had had Indian Ocean dipole events more often and more strongly than over their proxy record, which went back further in time than this, which is how they can calculate it to be statistically significant. So they suggested that we will have more and stronger IOD events in the future, and also that the way it interacts with the Asian monsoon will also change, which could have quite large impacts for Northern Australia, India, and Africa as well, in terms of rainfall. Okay.
What did you call IOD event?
So
Positive or negative?
when it has that particular pattern. So sometimes it doesn't have that pattern, so you'd say the IOD is not strong, like the index is neutral. But when it has that particular pattern, then your index is going to be like strongly positive or strongly negative, depending on the sign of it. So basically, this pattern's appeared more often, more recently.
But it's not like a sine oscillation, there's stays positive and then stays negative for some time.
Yeah, so it's not regular. It's not a regular oscillation. It'll come for the timescale, I think about a year, and then this period. It's a little bit like ENSO in that regard, which we'll talk about now. So the El Niño Southern Oscillation, living in Australia, everybody has heard of this, I assume. So first of all, I'll talk about the normal circulation of the equatorial Pacific, and then we'll look at what it looks like under an El Niño event. So we have winds blowing across this way, the trade winds, and they cause warm water to be piled up over here in the warm pool, and upwelling from colder, deeper water over here to make the cold tongue. Associated with that, you have a circulation in the atmosphere. What that means in the ocean is that the thermocline is sloped. So if you think of the thermocline as the border between the warmer surface waters and the deeper cold waters, because it's warm over here, there's more warm water, so your thermocline is deeper and shallower on this side. So naturally, across the equatorial Pacific, the thermocline has a slope. If you look at what happens, firstly during La Niña conditions, the winds speed up. That causes the warm water to be pushed further over here and further upwelling. So you're basically increasing the slope of your thermocline. So you're exaggerating the natural warm pool to be stronger and the cold tongue to be colder. And the opposite under El Niño conditions. So the thermocline relaxes, the warm water ends up more over towards the coast of South America. So that you have changes in the thermocline slope, the wind strength, and the warm water volume. What that looks like, this is the neutral conditions. You can see the warm pool and the cold tongue. This is the anomaly that happens during an El Niño. You end up with a much warmer cold tongue. And this is the anomaly during a La Niña. You have an extra strong cold tongue, basically. If you look at the time series, so what people do is you calculate SST over a particular box over the equator, and you make a time series of that. And so when it's positive, you're having an El Niño, and when it's negative, you're having a La Niña. And you can see a few interesting things from this. It's not exactly regular. It's sort of every 2 to 7 years or something. El Niños tend to be stronger than La Niñas, and also La Niñas tend to occasionally persist a bit longer. So here, for example, 1997-98, there was a really large El Niño, and then after that, for a couple of years, the La Niña just sort of hung around. And that tends to happen more with La Niñas than El Niños. So it's not symmetrical, basically. And it is phase-locked to a particular time of year by the seasonal cycle. So if you look at the way where's that wobbling? This room is haunted, I tell you. We have voices. So if we look at the time series by month of this index, you can see that it always peaks December, January. Same for La Niña as well. So these are all things that, if we're modelling it, we would like to be able to model the asymmetry and the seasonal phase locking. So I have another movie. So this is another one done by NCI on ENSO, and there's a creepy voiceover which we have turned off successfully. Okay, so we're looking at sea surface temperature, and you can see also it's not flat, so they've put in sea surface height as well. You can see the warm pool over here and the cold tongue over here, and also lots of cool equatorial waves sort of propagating around. And now the world is exploding. They take out a section here, so you can see the thermocline slope. There you go. So you see this rapid change in temperature, that's the thermocline. So you can see it's shallower over towards east. And now we're having an El Nino, judging by this little counter over here. You can see the thermoclines are lots flatter. This warm water is coming over here as well. Then as we go back towards neutral conditions, the slope goes back to what it normally is. And then when we go to a La Nina, you have a lot steeper slope, so more cold water close to the surface over here. And this was the 97, 98 La Nina as well, if you look at the little clock. So if we wait, here we go. Now you're looking at not temperature, but temperature anomalies. So you can see the anomaly along the thermocline by the displacement of the thermocline. And yeah, it's a little bit slow, so I'm not going to play the whole thing. Okay, so the other thing about El Nino is it's not always exactly the same pattern that is appearing. People have divided it into two general, they're called flavours, two flavours of ENSO. So the normal one, what we think of as the normal one, is the Eastern Pacific pattern, where the largest temperature anomaly is over against the coast of South America. But there's also another one, which is called the Central Pacific pattern, or El Nino Modoki, because it was discovered by Japanese researchers. And Modoki means same but different, which is pretty cool. So it's still an El Nino, but it's slightly different. So the largest temperature anomalies occur over in the middle of the basin. So the reason I'm telling you about this is because that is one of the things that might change in the future under ENSO, that we'll get more of one type or the other. But we'll talk about that a bit more later. First of all, the impact. So this map has divided up the impact by El Nino and La Nina. They're mostly symmetric, but not exactly, and by month. So this is during the peak of the El Nino over summer, and this is the other half of the year, basically. So some things that you would expect when you have an El Nino, you have more, it's warmer over here, so you have, for example, wet and warm conditions, and it's colder over here, so you end up with dry conditions, because it's also, it's not only an ocean phenomenon, which I sort of keep forgetting, it's also an atmospheric phenomena, so you're moving the main convection regions along with the temperature anomalies, so you're having a big effect on rainfall over here. But it also has effects further away. So California drought, for example, they've been in the news periodically for having droughts and then having floods and then having droughts, just as we are, I guess. That's usually linked to the phase of El Nino. Yes, next. So rather than talking about how ENSO is going to change in the future, I am first going to talk about the Interdecadal Pacific Oscillation, because as you will see, they're quite linked, so I'll talk about that at the end, future changes. So the IPO, or PDO, is a pattern of sea surface temperature variation over the whole Pacific. You have this large warm anomaly here. So this is the positive phase of the IPO, what it looks like in SSTs. There's a positive phase, positive temperature anomaly here and negative here. You see this looks quite a lot like ENSO, but it also extends further into the north and to the south as well, which is why it's considered to be a different mode. It's not just ENSO. And the contours on top of that are sea level pressure, so it's also linked to the Aleutian low here, changes in its strength. If you look at the time series, this is from 4 different data sets. You see that it is a lot lower frequency than ENSO. So ENSO was like every sort of 2 to 7 years. This is a much more decadal signal. And you can also see that in the lag. This is a lag correlation, like the autocorrelation between the PDO and itself. So you can see that it persists for it's 18 months. So it's much slower than ENSO. this is a little bit of an aside because I found it when I was looking for plots, and it's a really cool kind of plot. So if you don't know about it, then this is your opportunity to learn. It's called a Taylor diagram. There's a paper by Taylor in 2001 that explains it all. And basically, it's a tool to look at how well different things agree with each other, like spatial patterns. So it's not just taking two time series and correlating them, it's also taking into account spatial patterns and standard deviations. So for the angle, you have the correlation. On the distance from the origin, you have the standard deviation. So here, for example, that black circle is one particular observational data set. We had ISST. The IPO pattern that is calculated from that data set. And then the distance from that is sort of the agreement between all the other data sets here, these three. The same data set when you change the southern boundary of your region, and then these three sets of models. So the closer they are to this point, the more they agree, basically. But you're also looking at correlation and standard deviation as well, so it gives you a sort of broader picture. So if you ever have to compare data sets and spatial patterns, go and look up that paper. It's really cool. So basically what it's showing is that there is a little bit of variability between the data sets. They don't all exactly agree on what the spatial pattern should be, but they are pretty close, much closer than, for example, the models, which are all over here. And it has a bit of an effect where you set the southern boundary of your region to be. So this is why people argue about whether or not there is a difference between the IPO and the PDO, because the PDO, you set your boundary somewhere in the northern, I think 20 degrees north, whereas 70 degrees south, I think that's the diamond there. So there is a little bit of difference between the spatial patterns calculated. Okay, so what causes the IPO? And why does it have a long time? Like, why is it so slow, basically? Part of that is what we call the re-emergence of ocean temperature anomalies. So this is ocean temperature with depth over time after the peak of an IPO event in three different places, in the northern Pacific, the central Pacific, and the western Pacific. And what you can see, particularly, say, in this case, you have a temperature anomaly that goes quite deep, and it disappears at the surface, but then it reappears the next year, next summer. So why that is because, so this plot, this line here, which goes up and down, it's the seasonal mixed layer depth. So you can see in winter, the mixed layer is very deep, and then it shallows in summer, and then it deepens again in winter. So then what happens when it deepens? So the temperature anomaly disappeared in summer from the surface, but when it was still present at depth. So when the mixed layer deepens again the next winter, you're sort of mixing that colder water, that anomaly that was still there from the last year, below, back up to the surface. So if you're just looking at the surface, you have a temperature anomaly appearing, disappearing, appearing, disappearing. Whereas if you look at depth, it's still there. So basically, as soon as your anomaly gets deep enough, it's going to be longer lasting because it can reappear the next year. So that's one of the theories of why the IPO is persistent. And there's a lot of talk about what causes the IPO. A lot of people think that it's just this re-emergence effect from ENSO anomalies. And then there's people who link it a lot more to atmospheric pressure in the northern hemisphere. So what this paper here did was take three of the main contenders, this North Pacific sea level pressure variability, the Central Pacific ENSO and the Eastern Pacific ENSO, so the two different flavours of ENSO that I talked about, and reconstruct the PDO from that. So it's not exactly a settled answer. There's still quite a lot of debate about what exactly causes the PDO. And so, of course, there's going to be a lot of debate about how it's going to change in future, because if we don't know what causes it, we can't exactly answer how it's going to change. But these are the main contenders, so North Pacific variability and ENSO. And yeah, that's basically what that says. So the IPO in models, I showed you the Taylor diagram before of the scatter of the models, but here's just an example. Here's a model that does it quite well. It looks a lot like the plot of observations I showed you, this wide sort of tongue of warm water and negative blob over here, and it's kind of symmetrical but a bit weaker in the southern hemisphere. Here's a model who does it badly. It's sort of missing the whole equatorial and southern ocean bit. It's just really restricted to the northern hemisphere. So if you were studying mechanisms of the PDO in these two different models, my suspicion would be that here you'd think ENSO has an effect, and here you would think that it all just depends on whatever that sea level pressure is doing. So it's a bit of a warning that if you're studying something in models, you have to, well, take it with a grain of salt, because the mechanisms can be actually different in the different models. Okay, so here's a recent study of predictability of temperature due to the IPO. So this is a plot of observed surface temperature up until 2016, and then an estimate from models of what that temperature evolution is going to be like. So this is for global mean surface temperature. And what they're looking at in this paper is when we're going to reach the 1.5 degree C global temperature rise that was the target of the Paris Agreement. So the Paris Agreement's aiming to stay below that, but I think we all know that it's not totally pessimistic to say that it's not going to happen. So this is just all models. They've made this small adjustment here based on the fact that last year there was a large ENSO event, so they've done a small, just to take into account the effect that the ENSO had on the global mean. So they're starting from what they think of as sort of neutral temperatures and then increasing into the future according to what the models are showing. But then if you divide your models into those that are having an IPO positive phase or an IPO negative phase, you can see that it actually makes quite a difference. So the ones that are having IPO positive, their global mean surface temperature is a bit larger than average. The ones that are having an IPO negative, it's a bit smaller than average. So that the time that we reach that target, there's a difference of, 4 or 5 years there. So that's quite interesting, because this is the sort of timescales we're interested in doing our predictability for. So the IPO is obviously something we need to take into account, that if we're having IPO positive phase, it's going to be, temperature's going to be rising faster than if we're having an IPO negative phase. And that's what this plot shows. If you divide the CMIT5 models up by their temperature trend, depending on whether or not they're having an IPO positive or negative, the two distributions are distinct. So IPO positive is associated with higher temperature trends. And if you look at the hiatus that everyone got very worked up about, the slowdown in global temperature, that was this line. So that's right in the middle of an IPO negative sort of phase. And then the acceleration that was before that was associated with an IPO positive phase. And that's shown again here. So this is the time series of the IPO. This is global mean surface temperature. So the red bands are just when the IPO is positive. You can see that's when we were having a bit of an acceleration. Then the IPO is negative. We're having a hiatus. Here the IPO was negative. Temperature wasn't rising. Here the IPO was positive, and again you're having this temperature increase. Okay, so if we look at surface air temperature trends, 1992 to 2011, that looks like an IPO negative pattern. And that's because this bit, we were in an IPO negative pattern. And the same thing for sea level rise. You've probably seen this plot yesterday. If not, you'll see it a lot because it comes up a lot, that we're having much higher than expected sea level rise, much higher than average sea level rise in the poor Pacific Islands over here. And that is, we can associate that with the temperature anomalies associated with the IPO. Okay, now coming back to ENSO. So I've talked a lot about how a changing mean state will change a mode, the way a mode behaves. And that is something we can actually see in observations for ENSO, because if you think about it, the IPO is the background state for ENSO, because they are occurring in the same region but on different timescales. So here they've divided up past ENSO events by whether or not they happened in a positive or a negative IPO phase. They call it the PDO. So this is, on the top we have the high, like positive IPO phase, and on the bottom we have the negative IPO phase. And you can see in the positive phase, El Niño is much stronger than in the negative phase, and La Niña is weaker. So they've combined, basically, to give you a stronger or weaker El Niño signal. So there's been a lot of work done on what changes will happen to IPO and ENSO in the future. And as I said before, for the IPO, we don't really know that well yet. For ENSO, we can sort of make some predictions based on how it changes in different phases of the IPO. So ENSO is affected by mean state changes, but ENSO also changes the background state, which is called rectification. So that also means that changes in the IPO will also be affected by ENSO. So you can't study one without the other, basically. Something that makes it more complicated for ENSO is that we talked about how it's not symmetric, but also the dynamics of the extreme events seem to be quite different to the dynamics of the moderate events. So it's almost like you have to study two different things. The extreme ones don't always behave like a moderate one, but stronger. They actually have different processes that are getting involved. So, I'm nearly finished. So there was a nice study in Nature Climate Change a few years ago where they pulled a lot of this research together, and what these plots both show is in blue the control period, the anomalies, so basically the ENSOs that occur in a control period, and then in red the ENSOs that occur under a climate change scenario. And if you sort of look, you can see that both extremes get stronger under the climate change scenario. So we're expecting stronger El Niños and stronger La Niñas. The problem was it's not statistically significant in this study. So it's sort of pointing you in a direction, but it's not proof, definitely. But there are several things in the tropical Pacific that we know are going to change under global warming. We expect a weakening of the Walker circulation, and also the warming is not homogeneous, so it's not like we're just adding 1.5 degrees to the sea surface temperature everywhere. It is associated with a pattern. So that is going to have an effect on the stability of ENSO. So these mean state changes will modify ENSO and its feedbacks. The problem is that the feedbacks are quite model dependent. So some models will show one type of change and another models will show another type of change. One thing that they think is sort of consistent across models is that the frequency of ENSO events will increase. And that's what's shown in this plot. So the black dots are under current climate, the blue dots, and in this one the red dots are under future climate. So the top one is looking at just El Niño events, so that the extreme of, like, an extreme of the size of the 1997-1998. And under the control climate, they find it happens about every 28 years. Under the climate change scenario, it happens more like every 16 years, so the frequency is going to increase. And this one is looking at extreme ENSO events combined with extreme IOD events. Because the 1997-98 event was not only a strong ENSO, it was also a strong IOD. So they find that those events are also projected to increase from once every, 187 years to once every 48 years, which is quite dramatic, really. Okay, so once again, I've talked a lot. So I had a little bit about volcanoes, because if you compare global mean surface temperature rise with volcanic eruptions, shown by these spikes here, you can see in the models, on average, you always get a dip where you have a volcano. So basically, the volcanoes are spewing a lot of aerosols into the air, which temporarily reduces global mean surface temperature. So there was a study that, since we're looking at hiatuses, that looked at the causes of hiatuses and found that a lot of them were associated with volcanoes, and they had this particular pattern. Some of them were associated with aerosols, they have this particular pattern, and some of them that were not associated with either, that had this particular pattern. And all three of those patterns look kind of like the IPO. So that's, I mean, these ones, that is the IPO, because we already looked at how changing the sign of the IPO will affect global mean surface temperature. But these two also have that kind of spatial pattern, and so that sort of points towards some sort of more fundamental ocean dynamics. There's something about that pattern which just keeps popping up again. Yeah, I think that's everything. So, just in summary, to remind you all of what I just talked about for an hour, we have these different modes of variability, and we're interested in them because they add to the potential predictability of the climate system. So if we can understand these modes well enough to predict them, we should be able to predict our climate, at least on the shorter terms, a lot better. But how these are going to change in future depends on the background state, which we know is changing. And yeah, I don't really have concrete answers for any of the questions because we're still working on them. So thank you very much. And I am sorry for eating into your lunch break or morning tea break.
Simple question. What are the differentials, the typical differentials for negative and positive IOD or IPO?
So you mean when do we decide that it is an event?
Temperature difference.
That depends on different people define it differently. So if I go back to, where is it? Oh, further away than I thought. This one, for example, they've, Esteban, this is his plot. So they've drawn the line here. So it's when it's more or less than 0.5 of a degree by that index. Some people will do it by standard deviation. If it's more than one standard deviation. It sort of depends whether you're more interested in the strong events or just the events in general. But there's no concrete definition for that.
Also, about ENSO, why do we have 4? I remember that we have 4 indexes.
Okay, so part of that is, where is that plot? This. So here, this is the 3.4 box, so people calculate the 3.4 ENSO index, which is probably the most commonly used. But you can see that that is going to have, if you're calculating that index for this type of event, it's going to be quite a different result to if you calculate it for this type of event.
Yeah.
So people use the Niño 1-2 region, which is right next to the coast, to look more at this type of event, and that index will calculate. So again, if you're trying to calculate, if you're trying to look at just ENSO events in general, you want an index which will calculate, will capture all of them. Whereas if you're trying to separate them by different flavours, then you look at different indices. That's why there are so many different ones floating around. And it's the same for the PDO, IPO. There are a few different ways of calculating that. It depends on sometimes what data you have available. Yeah.
Another acronym, if I don't know where it fits, and I think I've heard of the NAO. Is that the same as the AMO?
No. So the NAO is in the atmosphere. There's a pressure dipole over the North Atlantic.
Okay.
And some people associate it with the AMO, like the NAO, because it's in the same region, might be forcing the AMO, for example,
Okay.
Or the reverse. So you think if it's an atmospheric process, it should be faster. So if you're having like a low frequency signal in the NAO, maybe that comes from the AMO, or vice versa. It depends. If you talk to an ocean person, they'll say that it's the AMO forces the NAO on the longer time scales. If you talk to an atmosphere person, they might tell you the opposite thing. So they are possibly related, like forcing each other, but they're not the same thing.
What's the period, though, for the NAO? Which one has the longest?
NAO is pretty much white noise. according to me. Yeah, it's much, much faster variability, atmospheric variability. So the AMO is a lot like multidecadal, so order of magnitude different.
You showed a long-term trend from paleo reconstruction on SAM. Mm-hmm. Are there any other long-term trends in the other modes of your methodology?
So as far as I understand from paleo stuff, that is one thing that is quite difficult. Like trends are quite difficult because there are usually trends over time anyway as your coral gets older or your tree gets older or something like that. So unless you have a long continuous record, like the good thing about that SAM record was that the trend wasn't over the whole record. Basically what I'm trying to say, if the trend is over the whole record of your paleo record, then you don't necessarily believe it, because there are lots of other things that could be coming in. But because this one had a little bit of a time where it didn't have the trend, so yes, the answer is I don't entirely know, but as far as I'm aware, there aren't that many that are long enough to really properly.
You said that a lot of the change in SAM was related to ozone, but there was an increase since the 1500s.
Yeah.
Do you know why?
So that I have no idea. So I'm going the wrong way. So the increase in the last little bit was sort of steeper, if I remember correctly. Here. This little steep bit is probably largely because of ozone. The other part of it, I really don't know. Sorry. Yeah, we can't put that down to ozone because we weren't building fridges in the 1500s.
I just wonder how individual models go at capturing some of these modes of variability.
So it varies quite wildly. They usually, so if I'm going to generalize, they usually have something that looks like the mode, but it's not necessarily in exactly the same place or with exactly the same timescale. So for example, ENSO, most of the models have one, but sometimes it'll be too regular, it'll be every year, or too infrequent, every 10 years, or it won't peak. It won't be phase locked, so it'll peak in March or something rather than December. So what you find if you look at studies that are trying to look at a model ensemble and a particular mode in that model ensemble, they'll usually have some sort of ranking system. They'll go through and have a look. They'll say, okay, this is my bunch of models that does quite well at ENSO, and therefore I'm going to trust those results more than the other ones that didn't maybe do quite so well. But that's the point I was trying to make with the picture of the PDO, the two models that have quite different patterns. One has an anomaly in the Central Pacific and the other one doesn't. So potentially, if you looked at those two models, you would get very different results because obviously there's something quite different. There's something missing in one of them in the tropical Pacific. So yeah, there's a big range, which is why you need to do sort of model validation before you start looking. Does that answer your question?
Yeah. I don't know about predictability of these modes. Given
Yeah, so some...
in the short time, the short record we have
So predictability also varies a bit between models. For the AMO, that's probably the one I know best for that particular question. It depends on the mechanism of the model. Some will have a mode that is very oscillatory, so maybe with some damping, so it's very predictable. And other ones, the mode will be so highly damped it'll peak once and then sort of trail off. You don't get a lot of predictability. So the predictability is also linked to the stability of the mode in that particular model and potentially to the balance of the mechanisms if it's getting them right. So again, it comes down to the problem of we don't know. I mean, we don't have a data record long enough, and we don't know whether the models are exactly trustworthy. So.
Can you comment on the lifespan of ENSO in the future, like RCP 8.5 scenarios?
So it differed a lot between models. This is the answer to every single question. Some of the models had quite a large increase in the amplitude, changes in the frequency, and then other models would do the opposite. So that's why it's not exactly clear yet. Yeah, sorry.
And will that the RCP 815 scenario will affect the initiation phase of ENSO or the decay phase of ENSO on the measuring phase?
I don't know enough about it. Ask Esteban.
I think what it's for sure is that the extreme events are expected to be more different.
But what about the decay phase of what about the decay phase of
The termination.
Are they going to be shorter or the?
I think it's not. Sorry, it's also.
Oh, good. I'm not the only one who doesn't know.
But, yeah. As far as I know.
And is there any shift of the peaking months of ENSO in the future? Like right now.
I don't know, but I would not expect there to be, because there's pretty good reasons why it's like locked the seasonal cycle, right? Correct me if I'm wrong, but I wouldn't expect that to change. You'll have to read that paper, the Chai. It's a review of ENSO changes in the future, so read that one. All right.
All right.
Done?